Let's welcome Professor Chakrabarti on the stage for his session on frontiers between language and reasoning.
Hello, good morning. It's a pleasure to be here. I'll be talking about the frontier between language and reasoning. Unlike the amazing landscape portrayed in the previous two talks, this will be a bit of a zoom down into very specific details of language and reasoning. So while we enjoy the post-AI era, I'll raise a few pertinent questions about how humans understand language and how we connect language to our world and reason about the world. So let's start with a very innocent sentence. Washington reclined on a Barcelona and popped open a cold Newcastle. If you submitted this sentence to a traditional NLP system, say even in 2015, you'd get these kinds of parts of speech for various tokens in the input sentence. And if you push the system a bit harder, you'd get these structures of lexical relationships between different tokens of the sentence. So we know Washington is a proper noun, we know reclined is a verb, and Washington both reclined and popped, and what was reclined upon a Barcelona, and so on. But what are these things? Humans immediately want to map from what are these tokens into real-world entities and relationships. And there, we used to have far less luck than today. So if you went to the Allen NLP demo for their older, non-deep language processing system, they would still say Washington is the location, Barcelona is the organization, Newcastle is an organization. Those are soccer clubs, and Washington is the location. If you went to the Code NLP website, it would say Washington is a state or province, Barcelona is a city, Newcastle is an organization. But that's not really how a human would ever interpret the sentence. This Washington often slams, but it never reclines. And reclining on Barcelona would not be comfortable anyway. Newcastle may be very cold, but it's hard to pop open. So today, LLMs have mastered this completely. If you go and ask ChatGPT, what is Washington in this sentence, Washington is a person. You'll never make that mistake. However, even though both humans and apparently large language models understand this sentence in the regime of objects, types, and relations, there may still be some problems left. So a human or ChatGPT would understand that Newcastle is this beverage which can be popped open. Barcelona is a style of furniture. It's a modernish European design chair, which should be pretty comfortable, but it was only introduced in 1929. Up to this point, things are going great. And then ChatGPT, if you push it, would say, this is Washington. But Washington could never have reclined on this version of Barcelona, because this Barcelona was released only in 1929. So perhaps we are talking about this rather more handsome Washington. Maybe, maybe not. If your knowledge base has 500 Washingtons, it's unclear if in the current discourse, the Washington is any of them. For example, if it's an act of fiction, it might be a Washington that's not even in a knowledge graph. Language models find it very difficult to desist from making a commitment and say, I don't know, this Washington is not any of my known Washington. There's no evidence for that. So there are still a lot of gaps left, and this goes back to hallucination and overlay of prior knowledge with the current discourse and such issues. So we do want to understand the world in terms of abstract types, a person reclined on a furniture and popped open a cold beverage. So for years, many of the most famous names in artificial intelligence have hypothesized that the human brain has a graph reasoning module, just like arithmetic module or logic modules. And fMRI scans have shown that very different regions of the brain are activated when different kinds of functions are going on. And this, again, is unnecessarily conflated in single language models. What is a kind of knowledge graph or a graph reasoning module that you invoke when you understand the world there are entities which are nodes, and there are labeled relationships which are edges. And we also understand that these nodes and edges might have temporal character, that people are presidents of countries within some time ranges, and so on. And other people may occupy the same position at a different time. In terms of digitally stored knowledge graphs, there have been a sequence of them through the decades. And today, in the public domain, some of the largest ones are Wikipedia and Wikidata. They have hundreds of millions of entities, several billion edges as facts, and hundreds of thousands of relation types. Wikipedia has almost 7 million entities, and 500 plus articles are added per day. There are millions of categories and hundreds of millions of internal hyperlinks richly connecting this space of entities. And these have been extensively used in natural language processing and continue to be used today. And yet, if you ask ChatGPT, how many nations have more rivers than Venezuela? ChatGPT will give you a very roundabout answer saying, this is how you go about doing it. But ChatGPT is in a position to see all of Wikidata and Wikipedia. How would a human navigate these knowledge graphs, collect the necessary information, and make an estimate? There may always be some errors in the margin, like do you really regard this stream as a river or not? But broadly, it should be possible to answer that question with some error bands. And as of today, ChatGPT can't do that, or at least last night. How would humans do that? And I was actually shocked to find an updated estimate of the human brain power. It's apparently just 20 watts. Apparently, the body at rest consumes about 80-85 watts, of which 20 watts are in the brain. Have you ever read Wikipedia end-to-end? Me neither. Do you have Wikidata incorporated in the structure of your neurons? Probably not. Do you need 5 examples to solve simple cognitive tasks? Not really. Do you hallucinate? Oh yeah, but it's a little different from LLM's hallucinations. So it seems like for humans, the recipe of accessing knowledge and processing it is our primary strength, not the knowledge itself. Right? So dynamic retrieval and linkage are the keys. And not really how much information is stored in the language model. So today I'd like to argue that human cognition and reasoning goes far beyond language, and it's vital to combine it with logic systems as well as graph-structured understanding of the world. So here's one motivating example of the kind of problems you might want to solve or can solve once you're armed with both language and graphical understanding of the world. So suppose there's this query, the birthplace of a cricketer, I want to find the birthplace of the cricketer who led the winning team in Adelaide in 2003. There are some ambiguities, like winning team at what sport. But modulo that, there's cricketer, so it's likely to be cricket. And cricket is often played in Adelaide, so that's good. There's some reinforcement there. So we say, look, I'm looking for entity U1 whose type is location because it's a birthplace. And in particular, cricketer E2 was born there. Because there's the keyword led, you would expect that cricketer to be involved in an act of captaincy. And captain is of a team, so winning team, so E3 is the team. And that happened in Adelaide, that event of victory, and it happened in time 2003. And then there's world knowledge, which says to lead a team to victory in a particular match in 2003, you have to be the captain in 2003. So there's a confluence there, which is world knowledge. So this graph basically is a very complex, but actually an implicit representation of the textual query I asked. And I'd like to argue that queries as graphs is as vital as passive text as graphs. And these graphs need to be matched up to get your correct answers. Meanwhile, there's this passage sitting out somewhere in Wikipedia or the web, which says Saurav Ganguly was born in Kolkata in 2003. Ganguly was captain of the Indian cricket team. This page or this paragraph is one of trillions of paragraphs on the web. To zoom down into it, I really have no clue. Apart from the 2003, nothing matches. But there are so many documents where 2003 matches. There's also this table somewhere on the web, which is an HTML table with no standard schema, where only from the other context in the page and maybe the table caption, we know that it's about cricket matches and their winners and losers. So there are columns which have some information. Now, Adelaide starts matching and 2003 starts matching. And maybe from the page context, I know this is about cricket. So now things are starting to warm up, right? And now the question is, how do I enable linkage between all these sources of information, the question, the table, and the text? There are techniques, and have been techniques for at least 10 years, which can take my passage and turn it into a little graph like that. So Saurav Ganguly was born in Kolkata, captain and captaincy. So now you see that it starts matching bits and pieces of the query graph. Meanwhile, the table has less help, but we know that there is something like a row, and it has columns, and Adelaide is the venue, 2003 is the year, India is the winner, Australia is the loser. Can I bring these three graphs together and identify the answer of Kolkata? So that seems still like a tall order. I need to understand that India in that table is the same as the Indian cricket team, and that's a non-trivial text bridging act that LLMs are now increasingly good at. And that this particular row in the table is actually a victory event. That may be even harder. Now, if you go and ask these questions of ChatGPT today, you might get the impression that all this formalism is unnecessary. It's already answering you correctly. But that's a bit illusory. Experiments have been done in asking these kinds of multi-hop reasoning questions, where the final answer given is correct, and then you drill down and you ask about specific sub-problems, and many of them are not nailed correctly by the LLM. There was actually a study from NUS, I believe, by Anthony Tang's group, which did this work. So to have explainable AI, we need all the steps to be described to someone at least reasonably trained in the art. Otherwise, you're never sure why the language model is getting it right. Here's another example that might have resonated with our speaker from Reserve Bank, Dr. Vasudevan. So there are lots of legacy tables like this, and even if you wanted to get it structured, you would need very complicated OCR and tables restructuring software to do that. And even in contemporary settings, you might have huge amounts of reports coming into ACCI or SEBI and so on, right, with tables that look like this. And the question might be, in 1997, what fraction of lima beans planted was harvested? It's a highly non-trivial visual grammar for extraction and processing. For example, 1997 and planted together creates this pattern, from planted to 1997 and down the column. So the human eye, if you could track our gazes, you would see that we would scan for 1997 and planted, and we'll scan down the red rectangle. Similarly, harvested in 1997, you would scan down the rectangle, and those would form your initial focus of or foci of attention. And then lima beans are involved, so now you scan for lima beans, and that creates a row-wise attention. And the way we would process the document is that we would look for extracting the two values, 2700 and 2500, and those would be those marked cells, and the values would be, say, $1 and $2, and then we have to compute an expression. This is really the whole explanation of how things should go. Not from the LLM's packaged memory, but from here. Why is this important? Again, with regard to the RBI talk, the LLM might have been pre-trained in a different country with a different legal regime, which talks about regulation and enforcement of business practices under a different set of laws. Those have been baked into their language model. And now we have a different legal code. We don't want any leakage from there into this setup. I want my answer to be coming from this table and not preformed opinion of how lima beans are harvested in the LLM. So the recipe consists of starting with a table and a question, have an extraction plan, And I should be able to explain it to anyone. A human answering the question, if they're asked, they would say, look, I looked at this and the cells at the intersection of those rectangles are the values I should extract. And then, when the values come out, I need a computation plan with them, and the computation gives me the answer. We absolutely need to insist that the next generation of AI can provide all these steps. Chains of thought do a lot of this, but not quite enough, especially in the multimodal setting. The grammar of charts and diagrams to extend beyond tables. So here's a question. Find a paper that reports the best trade-offs between response time and ranking quality for dense retrieval systems. To do this, I need to go into archive, the main computer science paper repository, and from millions of papers, somehow nail one of the best papers to answer this question. From that paper, extract this diagram, use world knowledge to understand that flops is floating point operations, and the more flops there are, the slower the query, so the larger the response time. So the left part of the graph is better for me in terms of response time. On the other hand, ranking quality is represented by mean reciprocal rank, or MRR, and higher MRR is better. And therefore, the region I should zoom on is that upper left corner. And if you look at the legend, or the marker at the upper left corner is the blue circle, my gaze shifts downward, I find distill-splayed, and then I report that as the answer. The distill-splayed algorithm may be with a citation and a GitHub code page saying, go to this paper and this code to find the system that gives the best trade-off. Bibliographic search today is completely hobbled. It's nowhere near this level. Extending to less controlled images, suppose you have a query image where a man in a shirt is riding a horse. There is technology to identify regions in images, make a little functional and layout graph out of that, and based on earlier association between text and videos and images, like we were listening about, you can actually infer that the man is riding the horse and not, for example, feeding the horse. So based on that, for either images as queries or text as queries, we should be able to have much better quality of ranking of images or video frames, where the exact same functional relationship hold between the elements of the image. Then there is cross-modal querying of the form, I give you this disturbing picture, and then I ask this, what are these animals poached for? So how do I answer this question? Again, not as an end-to-end miraculous act, but as how human brain can deal with this problem. So again, visual object recognition will tell you that in this picture there's a gun, there are trees, there's in fact a jungle, an elephant, and some people. And remember my knowledge graph. So from the knowledge graph, we know that there are animals of various forms, and elephants and humans are both mammals, but only some humans are poachers, right? So based on that, so now connections start building up. Animals links to animals, and poacher matches poached. So some part of the knowledge graph heats up. So besides, on the Wikipedia or on the web, there are passages like this. Poachers kill about 20,000 elephants every single year for their tasks. And for matches for, although it could be a more indirect match. Right? So once again, it's the case of billions of documents, hundreds of millions of nodes in the knowledge graph, but there's only a certain pattern of connectivity which reveals the answer to you. So once these connections are built, poachers, between the passage, the knowledge graph, and the image, and the question, we can now edit the question and say, what are elephants poached for? That's pretty obvious at this point. And once you ask in this form, it's great for an LLM to answer. It's easily going to extract the correct responses, and there are tasks and ivory. But we need this initial helping hand to build the bridges between all these communities. So at this point, I hope I have convinced you that from a multitude of applications and modalities, it's essential to know how to join and match up graphs to each other. So that's the premise of the talk. So today I don't have much time to go into our technical work or algorithmic work, but I'll take some baby steps and hope to keep all of you with me. So as a baby step, we'll talk about graph matching. Graph matching is a notoriously difficult combinatorial optimization problem. But in the context of trainable distributions of graphs in real life, how well can we do, say, based on neural networks? So here, n-node graph, n is equal to 4 in this graph GQ, can be represented by a 4x4 adjacency matrix. At the moment, I'm pretending as if the nodes and edges have no features to keep the conversation simple. But of course, these nodes have a lot of rich features, and the edges have a lot of rich features corresponding to entities and relationships between them. Now, nodes are numbered 1 through 4, and the rows and columns of the matrix are also numbered 1 through 4. Connections are denoted by a 1, lack of connection is a 0. So that's the graph. The matrix AQ fully represents the graph GQ. I'm given another graph in the corpus, say, where all the edges in GQ exist and some more. The edge 2 to 3 or 3 to 2 is extra. So we say that the graph GQ is a subgraph of GC because it embeds completely in GC with some edges possibly left over. And this has applications in many areas, knowledge graph matching, even searching for molecules, what enzymes dock to what proteins, and all that stuff. Right. Now, we say that GQ is a subgraph of GC if the adjacency matrix AQ is element-wise less than or equal to the adjacency matrix for GC, that's AC. So as you can see, there are places where GQ has a 0 and GC has a 1, and that's fine. Because that's what we are looking for, that GQ is a subgraph of GC. Every edge in GQ is also present or covered by a corresponding edge in GC. But this is not how nicely graphs will be given to us in reality. What if the nodes of GQ are presented in some arbitrary order? Suppose we want to draw GQ in a different way, where 1 maps to C, 2 maps to A, 3 maps to D, and 4 maps to B. Then the same graph is reordered in the matrix form to have zeros and ones in a different position. Right? And this time there are ones, the red ones, which are not ones in GC, and unless we can reorder the nodes of GQ prime, we'll not be able to say that GQ is a subgraph of GC. We cannot do it simply by comparison. Before testing, we must apply the inverse permutation to the rows and columns. Right? To test if, and this can be done by multiplying and before and after by a permutation matrix. If there's a permutation matrix P corresponding to this transformation, and we multiply AQ prime before and after with P and P transpose, we can still test it. This is easy to verify. But the question is, who's going to propose or give us this permutation matrix? So the inputs are the raw adjacency matrix AC and AQ prime, and there is some unknown network which has to output an approximation to an n by n permutation. So this is tricky because for the longest time, neural networks output an approximation of 1D logits, right? So a language model samples and output vocabulary. So we start with a logit, we take a softmax, and you get a multinomial distribution over a 1D space. How do we extend that to a permutation? There are ways to do that. But how do you want to train this? So suppose there's a GQ. We say that GQ is a subgraph of GC plus, that GC plus is a desirable graph if this property holds, right? Whereas there's also a negative graph, GC minus, which we don't like because there doesn't exist any permutation for which this inequality will hold. So in one case, there exists a P such that this happens. In the other case, there is no P for which this relationship holds. And human supervision will only want to supervise with GQ, GC plus, and GC minus. Like we're hearing about pairwise preferences versus listwise preferences. We only want to say, for this query, I like this image. For this query, I think Kolkata and Saurav Ganguly are the answer subgraph, but nothing else. And then from here, we need to, while training, also infer the certificates, the permutation matrices, which help me learn that pattern. So I don't go into the scary diagram. This is how we can train a neural network to learn how to find the certificates P and also find whether GQ is a subgraph of GC or not. So I said that these graphs are richly featured, and here's another application of that. So suppose we want to align knowledge graphs across multiple languages, and this can be very valuable in growing our knowledge graph with information which was not originally in it. So we have been talking about supporting multilingual language models, but to do that, you have to start with first aligning multilingual knowledge graphs so that they can accumulate knowledge into the language model. In English, you might say that there is a fact triple Albert Einstein, place of birth, Ulm. But in the knowledge graph Wikidata, there are actually abstract IDs, Q937 for Albert Einstein, P19 for place of birth, and Q3012 for Ulm. Those are opaque IDs. If you click on these, you'll go through to the page on Wikidata, which will list you all the properties and the connecting relationships. That same fact triple in Hindi would be written as Albert Einstein, Janmsthan, Ulm. Observe that Albert Einstein and Ulm are just transliterations, whereas Janmsthan is a translation of place of birth, and that's an important distinction. So in real life, mappings between knowledge graphs are always a mix of translation and transliteration. So at this point, suppose we have the Hindi table and the English table. We want to verify or we want to infer if the Russian Stolitsa or Hindi Iski Rajdhani is the same relation as capital of in English. So how do you do that with some confidence? So there are existing techniques which can embed every entity in a knowledge graph to a vector and every relation of a knowledge graph to a vector. We can compare the embeddings of the relations to decide if the embeddings are sufficiently close that these relations are the same. But that's nowhere as good as judging a relation by the company of entities it keeps. How do we understand a relation, right? So the relation capital of is characterized by pairs like India, Delhi, Japan, Tokyo, Austria, Vienna, and so on. Meanwhile, the Hindi table has Chile and Santiago, those are transliterations. Japan and Tokyo are also transliterations. But instead of United Kingdom, it may have Yukt Rajya. So again, it's a mix and very soft matching between these. So it's better to collect the subject-object signature, SO, of a relation, turn it into a set of vectors, and then try to align this set of vectors. And that gives a much better performance. So I've just tried to give a couple of vignettes of how graph matching and graph alignment can build bridges between queries as graphs, textual corpus as graphs, tables as graphs, images as graphs, charts as graphs, and so many other modalities. So we believe that graph alignment and graph isomorphism can form a very sound backbone to these kinds of inferences. Many of the legal codes underlying finance, banking, can actually be encoded in knowledge graphs. Many of the medical knowledge has been successfully encoded in knowledge graphs. Materials. Increasingly, there are slices of human knowledge which are being codified as graphs. And to try to mitigate further the problems of generative AI and large language models hallucinating or having an excessive amount of confidence in finding a solution to your problem or answering queries that should not be answered, it's often a result of the textual knowledge not sufficiently allied or aligned to codified formal knowledge. And we are hoping that this line of work will mitigate that problem. So reasoning involves many other brain modules and regions than language representation, interpretation, and generation. Language is one of the things we do. We do many other things with our brain. Natural language is not the best to represent all these forms of reasoning. Formal logic was invented for a good reason. And in fact, with the rise of agent systems, we are actually returning to that space saying it's probably not best if agents interact with each other in natural language. Why are we calculating using an LLM? We shouldn't do that. They have a very specific structured language of interaction. There's an area called semantic interpretation where noisy human language is translated into more precise query language like SQL or Sparkle, which are then the interchange media between formal agents. And there needs to be more work in that space. In this talk, as I was saying, I have focused on graphs and tables as critical representations used to communicate reasoning steps between humans. If I want to convince you I got the right result, I need to show you the steps using a point and tell on the layout of the text, on the layout of the table, what values I extracted and what operations I did with it. Tables can themselves be represented as graphs, and much world knowledge is already encoded as graphs. And the retrieval problem is also extremely significant. There are language models now which support increasingly longer context lengths. But are longer contexts necessarily a panacea? Probably not. There are papers which show that long context cannot be uniformly and effectively used. There's a nice paper called Lost in the Middle, which shows that in a long prompt, if the answer is somewhere in the middle, it's much more likely to be missed as compared to the beginning and the end. And the sample complexity of training the LLM to be equally sensitive everywhere in that range is just too much. So we have also found in our experiments that just because we can cram a lot of information into a long context, maybe we shouldn't. There's a vital step of retrieving relevant subgraphs from this gigantic billion node union of all graphs of human knowledge, which really form a coherent subgraph that the language model can then make the best use of to generate your answer or to infer your answer. So even the top language models need to learn this skill to avoid the current problems of hallucination or lack of alignment. Thank you for your attention.